So how
So
would you do
again,
the
I'll
next?
repeat, for problem 3 in section 1.2, the graph of the exponential function looks like this, and every real number, every positive number is e to the x for some x. Just as if you look at the graph of the natural logarithm or any logarithm, every real number is the log of some positive number. And these two graphs show it all.
Thank you.
Thank you.
Anything else?
Yeah, could we go over for section 1.1, question 4 and 5 on the cardinality section? Having trouble with that.
Section 1.1.
Yeah, so that's, let me see. Yeah, so question 4 says, let X be a finite set with cardinality X equal to N. Prove that there are 2 to the N minus 1 subsets of X that contain an even number of elements.
Right. So I did that this morning, and you can just check the video, which I think has been posted already. So it's based on the fact that the power set of a set of n elements has 2 to the n elements. And if you look at the subsets of a set, half of them have an even number of elements and half of them have an odd number of elements, because you have to prove that. And that implies that the number of subsets with an even number of elements is 2 to the n minus 1. But if you check the video of this morning's problem session, you'll see I worked out some examples, and then I worked it out, then I wrote it out in detail.
Professor, when you're making the video, can you just make sure that it's not in thumbnail view or gallery view? Because I looked at the video and I couldn't see it. It was like in a thumbnail. It's hard to see it.
It should be full screen.
It's not.
Well, I'll go back and double check, but you should also check how your settings are on your computer. And but it should be full screen. But we'll see. It may be when I'm trying to do this in a problem session with the whole class that it only records the thumbnail, but I'll double check. I'll see. Okay. So this is a problem about this binomial coefficient C of nk, which is the number of k element subsets of a set of size n. So part D says the following: show that if k1 plus k2 equals k, and n1 plus n2 equals n, then C of nk is equal to let's see, there might be, let me just double check this. C of n1 k1, C of n2 k2, and summing over all pairs of integers k1 and k2 that add up to n. Okay, so let me see what the idea of this problem is. So we have a set with n elements. And we want to know how many k element subsets there are. Suppose we divide this set up into two pieces. So this subset has n1 pieces, and this subset has n2 pieces, and n1 plus n2 is equal to n. Okay? Is that okay? Are there any questions about this first step? So you have to really have it clear in your head what C of nk means. It's the number of k element subsets in a set of size n. So this is my set of size n. And I choose two numbers, n1 and n2, that add up to n. And I'm going to divide this set up into two pieces. One has n1 elements and the other has n2 elements. And now, suppose I have a set with k elements. So this is my set in red, and it has k elements. And some of those elements are over here, and some of those elements are over here. So if the number of elements in the left side is k1, write that like this, and the number of elements in the left side is k2, then k1 plus k2 is equal to k. Right? So all I'm saying is, if you have a set with n elements and it's divided up into two pieces with n1 and n2 elements respectively, and if you choose a k element subset, some of those elements will be over on the left side and some will be on the right side. And what are the possible choices of all the numbers of k1 that can be on the left side? Well, k1 can be anything from 0 up to k, and k2 is always going to be equal to k minus k1, because it has to be that k1 plus k2 adds up to k. So I could say, well, how many sets of size k have exactly k1 elements in this left-hand side and k2 elements in the right-hand side? So the number of sets with k1 elements in, let's say I call this set x1 and this set x2. So with k1 elements in x1 is the number of ways you can choose out of a set of n1 elements k1. And the number of sets with k2 elements in x2 is C of n2 k2. So C of n1 k1 times C of n2 k2, this is exactly the number of subsets of size k which have k1 elements on the left side and k2 elements on the right side. And k1 can be any number from 0 up to n. k1 plus k2 is any way to write k as a sum of k1 plus k2. And if you add this up for all the possible values of k, this is exactly C of nk. So there's a lot of, I just wrote it down, it took a page in big letters and big pictures. But there's a lot of thinking that goes into understanding this proof. And until you understand the proof of this part of the problem, part D, you're not going to be able to go on to part E. In part E, it's just a generalization of this argument. In part E, you have this big set X. You have cardinality of X is n, and n1 plus n2, you choose R integers that add up to n. And you divide this set up into pieces, x1, x2, x3, up to xr, where x is the union of these sets, and the cardinality of the set x sub I is n sub I. And now you take a subset of size k. So this is your subset, and it has some elements in each of these pieces. And let's say you take a subset A contained in X, and the cardinality, or the number of elements of A, is equal to K, and you let K sub I be how many elements of A are in this part X sub I. So the intersection of A with Xi. You have to become familiar with the notation, the language of set theory. And summation K sub I goes from 1 up to R, equals K. And then after you've spent a lot of time perhaps understanding the argument in part D, then you can try and generalize that to get the argument in part E. But this requires time. That's
Professor, excuse me, sir.
Go
So
ahead.
in the I'm looking at the part E in the book, and it seems it's missing the summation notation, without which it wouldn't make sense.
You are right. Thank you. That's a typo. I will correct that.
Okay, because I was trying to do that and I thought it didn't make sense without the summation mark. But if the
No.
summation is there, then I understand it. Thank you.
Yes.
So what does that notation mean, Professor? I don't know. I've never seen that before.
Which
the
notation?
The one that looks like the 2 Roman numerals.
Oh,
And
this
yes, what is that?
means product, just the way this means sum. So if you write summation A sub I goes from 1 to 3, that means you sum A1 plus A2 plus A3. If you write this capital letter, this is a Greek letter sigma, this is a Greek letter pi, I goes from 1 to 3 A sub I, this means the product A1 times A2 times A3. So that's product notation.
Okay.
Professor, we're not seeing the bottom of the page, please.
Professor, one more question.
Go ahead.
In terms of homework, some of these questions are multi-part and some of them are repetitive. So is it okay if I just do some of them and not all of them?
You do as much as you can.
Okay. Coefficient, and I know the formula. So if we use a formula, then it becomes sort of like, fairly straightforward using probably using formula manipulation.
Let me write it down so everyone can see. So the number of subsets of size k in a set of size n, this is sometimes written as the binomial coefficient n over k like this. And this is defined to be n factorial over k factorial times n minus k factorial, where n factorial, this is written n factorial, is the product of all the positive integers up to n. And 0 factorial is defined to be 1. This factorial is just an exclamation point. So this is the definition of the factorial. And the formula for C of nk is equal to this. So if you were to write down C of n minus 1k plus C of n minus 1 k minus 1, that would be the binomial coefficient n minus 1 choose k plus n minus 1 choose k minus 1. And if we use this definition of this binomial coefficient, this is n minus 1 factorial over k factorial, n minus 1 minus k factorial. And this binomial coefficient is n minus 1 factorial over k minus 1 factorial times n minus 1 minus k minus 1 factorial. So this is n minus 1 factorial over k factorial n minus 1 minus k factorial plus n minus 1 factorial over k minus 1 factorial, and n minus 1 minus k plus 1, the ones cancel. This is n minus k factorial. So I have these two fractions, and I can put them over a common denominator. A common denominator would be k factorial times n minus k factorial. So here I have n minus 1 factorial in the numerator. And to get from n minus 1 minus k factorial to n minus k, I have to multiply this by n minus k. And I put this over k factorial times n minus k factorial. And here I have n minus 1 factorial times k. So now I have the same denominator. So I can add the fractions. I get n minus 1 factorial times n minus k plus k. And the k's cancel. So this is just n minus 1 factorial times n, which is n factorial over k factorial to n minus k factorial. So that's c of nk. So this is so if you know what the binomial coefficient is, and this is often done in calculus or pre-calculus, then you can prove just from the explicit formula for the binomial coefficient, you can prove this identity.
Okay, so I think that answers my question. I mean, that was a third approach that I was thinking about, but I wasn't sure whether we are allowed to use the formula itself or not.
Anything which is true is good.
Okay.
Proof means a proof. How you prove it is, so long as the proof is valid, it's fine.
Okay, thank you.
Anything else?
Can you quickly review number 5A, same question, please?
C of n1 is n and C of nn equals 1?
Thank you, yeah.
Okay. So C of n1 is the number of one element subsets of a set of size n. So if X is your set, and say it contains the first n integers, 1 through n, what are the one element subsets? The set that contains 1, the set that contains 2, up to the set that contains n. And here we have n sets of size 1. So C of n comma 1 is equal to n. They're exactly n one element subsets in a set of size n. And if A is contained in X, and the cardinality of A is equal to n, well, the only n element subset of a set of size n is the whole set. So the number of n element subsets in a set of size n is exactly 1. There's only one possibility.
Just to be clear, Professor, on your YouTube channel, I only see 2 lessons so far. One that was for yesterday, and the second is it says sets and equivalence relations.
Right. No. So what is up there at the moment are the 2 lectures from yesterday, and I still have to post the lectures for today.
Okay.
Okay.
Oh.
Anything else? All right. Okay, so let's stop for now, and I will double check and see whether there's a technical problem getting the problem session videos to fill up the whole screen. Okay. I will be uploading stuff this evening, and I will hope to see you, hear from you all tomorrow. Everybody take care.